Hey everyone, and welcome to Airwise Academy, your trusted source for ESA Part 66 learning. Today we'll be diving into Submodule 2, Mechanics, specifically Section 2, which covers kinetics. Our objective is to understand the fundamental principles governing the motion of objects and the forces acting upon them. We'll be exploring concepts like general motion, uniform motion, the crucial distinction between speed and velocity, and finally, acceleration. For B1 licensed engineers, the required knowledge level for kinetics is Level 2. This means you are expected to have a deeper understanding, be able to explain system functions, and understand how components work together. You'll carry out maintenance tasks, often with technical guidance or reference to manuals. For B2 licensed engineers, the required knowledge level for kinetics is Level 1. At this level, you need a general awareness and basic knowledge. You'll be able to perform simple procedures, but always under supervision. Let's start by defining motion itself. Simply put, motion is a continuous change in an object's position over time. If an object is at different places at different moments, it's considered to be in motion. You'll often hear the term force in motion. This broadly refers to understanding how objects move in response to applied forces. Within this, we have two key branches. Firstly, kinematics, which focuses purely on describing motion. That is, the relationships between velocity, acceleration, and distance without considering the forces involved. Secondly, and our primary focus for this section, is kinetics. Kinetics takes kinematics a step further by studying the relationship between the motion of bodies and the forces that cause that motion. So, while kinematics tells us how an object moves, kinetics explains why it moves in that particular way. Now, let's talk about a specific type of motion, uniform motion. This occurs when an object covers equal distances in equal intervals of time. The key characteristic here is that an object in uniform motion maintains a constant speed. This means its pace does not change. Think of an aircraft in cruise flight, maintaining a steady airspeed and heading, or a car using cruise control on a long, straight road. In these scenarios, the object is experiencing uniform motion. In everyday conversation, speed and velocity are often used interchangeably, but in physics, they have distinct meanings, and understanding this difference is critical. Speed simply tells us how fast something is going. It's a scalar quantity, meaning it only has a magnitude or a numerical value. For example, knowing an airplane flies at 150 miles per hour only tells you its rate of travel, not where it's headed. After 8 hours at 150 miles per hour, it could be in a completely different city or even back where it started if it flew in a circle. Velocity, on the other hand, is much more comprehensive. It not only tells you how fast an object is moving, but also in what specific direction. Velocity is a vector quantity, which means it possesses both magnitude and direction. So saying an airplane has a velocity of 150 miles per hour due north gives us a complete picture of its motion. Since velocity has both magnitude and direction, it's classified as a vector quantity. A vector is graphically represented by a line with an arrow. The length of the line shows the magnitude or the numerical value, while the arrow points in the direction that quantity is acting. One of the powerful applications of vectors is in vector analysis, where we can add or subtract them to determine net effects. A perfect aviation example is when we consider an airplane's velocity in conjunction with wind velocity. If you refer to the figure, you would see this illustrated. Vector A represents the airplane's intended velocity without any wind. Vector B represents the velocity of the wind itself, its speed and direction. When these two vectors are added using vector analysis, the result is vector C, which clearly shows the actual speed and direction the airplane will move relative to the ground. Without accounting for the wind, the airplane would not end up where it intends to be. Here's a crucial point that often causes confusion. Can an object have constant speed but changing velocity? The answer is a definite yes. This happens whenever an object's direction changes. Consider our airplane again, but this time imagine it flying in a circular pattern at a constant speed. Even though its speedometer reads a steady value, its velocity is continuously changing because its direction is constantly shifting. This is a fundamental concept for understanding motion. To calculate speed or velocity, the formula is straightforward: distance divided by time. The units will depend on the units of distance and time used. Common ones are miles per hour or feet per second. It's often necessary to convert between these units, and for that, remember the conversion factor. 1 mph is approximately 1.467 fps. While the calculation formula is the same for speed and velocity, always ensure to account for direction changes when dealing with velocity. Building on our understanding of velocity, let's move on to acceleration. Acceleration is fundamentally defined as the rate of change of velocity. This means an object can accelerate in three ways: speeding up, if its velocity increases, like a car merging onto a highway; slowing down, if its velocity decreases, which we often call deceleration; changing direction. Even if an object maintains a constant speed, if its direction of travel changes, it is accelerating. Think of a car going around a bend. Its velocity vector is changing direction. The units for acceleration reflect this change over time, such as miles per hour per second, mph per second, or feet per second per second. A very important constant to remember is the acceleration due to gravity, which is approximately 32.2 feet per second per second. This is the rate at which objects accelerate downwards when only gravity acts upon them. To calculate acceleration, we use a simple formula. Acceleration, A, equals the change in velocity, final velocity minus initial velocity, divided by the time it took for that change to occur. Let's apply this to an example. Imagine an Air Force F-15 fighter jet cruising at 400 miles per hour. The pilot engages the afterburners and accelerates to 1,200 miles per hour in 20 seconds. First, we find the change in velocity, 1,200 miles per hour minus 400 miles per hour, which is 800 miles per hour. Then, we divide that by the time taken, 20 seconds. This gives us an acceleration of 40 miles per hour per second. To express this in feet per second, which is a common unit in aviation and physics, we multiply by our conversion factor, 1.467. So, 40 miles per hour per second multiplied by 1.467 gives us 58.7 feet per second. Finally, we can relate this acceleration to g-forces. G-forces are a way to quantify how much acceleration a body experiences relative to the standard acceleration due to gravity. We simply divide the calculated acceleration by the acceleration due to gravity, which is 32.2 fps per second. In our F-15 example, 58.7 fps per second divided by 32.2 fps per second means the pilot is experiencing approximately 1.82 Gs. Newton's first law, often called the law of inertia, states that an object will maintain its current state of motion, whether at rest or moving at a constant velocity, unless an external force intervenes. This fundamental property of matter, inertia, is responsible for many everyday phenomena we observe. For instance, the classic magician's trick where a tablecloth is swiftly pulled from under a full setting of dishes is a perfect demonstration of inertia. The dishes, due to their inertia, resist the sudden change in motion and remain in place. Similarly, we experience the effects of inertia firsthand when an airplane comes to a sudden halt on the tarmac. Our bodies, still wanting to move forward, are thrown against our seatbelts. Understanding inertia is key to comprehending why objects behave the way they do in the absence or presence of forces. Newton's second law describes the relationship between force, mass, and acceleration. It states that when a force acts on a body, its momentum changes, and the rate of this change is directly proportional to the applied force. Momentum, a property of moving bodies, is crucial here. A body with great momentum, like a train, is difficult to stop even at low speeds due to its large mass. This law gives us the fundamental equation force equals mass times acceleration, F equals ma. This formula is vital in aviation for calculating thrust. Here we have a specific derivation for thrust which accounts for the change in air velocity over time. This formula is force equals weight times the change in velocity divided by gravity times time. Let's look at a practical example. If a turbojet engine moves 150 pounds of air per second and that air accelerates from 100 feet per second to 1200 feet per second, we can calculate the thrust. Plugging these values into the formula, where weight is 150 pounds, the change in velocity is 1100 FPS, 1200 minus 100, and gravity is 32.2 feet per second squared over 1 second, we find the engine generates 5,124 pounds of thrust. This directly demonstrates how the engine applies force to accelerate the air. Finally, we arrive at Newton's third law of motion, famously known as the law of action and reaction. This law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first. Forces never occur in isolation, they always come in pairs. Consider a simple example. When a man stands on the floor, his weight exerts a downward action force on the floor. In response, the floor exerts an equal and opposite reaction force upward on his feet, supporting him. This principle is fundamental to flight. For an aircraft propeller, the action is the blades pushing a stream of air backward. The reaction is the air pushing the propeller blades forward with an equal force, which propels the aircraft forward. Similarly, in a turbofan engine, the engine's action is to accelerate air rearward, creating a powerful jet. The reaction to this accelerated air is the forward force exerted on the engine structure itself. This is what we define as thrust. This law perfectly explains how jet and propeller engines generate the necessary force to move an aircraft through the air. Now let's see what circular motion is. Circular motion is simply when an object moves in a curved path, where the distance from the center of that path, known as the radius, remains constant. Think of swinging a weight on a string. Now, why does it move in a circle and not just fly off? This brings us to the concept of inertia. An object in motion wants to stay in motion in a straight line. So to keep it moving in a circle, it must be continuously pulled or pushed away from that straight path. This essential inward acting force is what we call centripetal force. It's always directed towards the center of the circle, like the tension in our string example. Without it, the object would indeed fly off tangentially. According to Newton's third law, for every action, there's an equal and opposite reaction. So, while the string exerts a centripetal force on the object exerts an equal but opposite force on the string, which we refer to as centrifugal force. This is often described as an apparent outward force felt by the object due to its tendency to continue in a straight line. Now, let's explore what factors influence the magnitude of centripetal force. There are 3 key relationships to understand. Firstly, centripetal force is directly proportional to the mass of the object. This means if you have a heavier object, you'll need a stronger centripetal force to keep it moving in the same circle at the same speed. It's a linear relationship. Double the mass, double the force. Secondly, it's inversely proportional to the radius. Imagine swinging an object on a shorter string versus a longer one. For the same speed, a shorter string means the object is completing tighter turns, requiring a much stronger inward pull to constantly redirect it. And thirdly, and perhaps most critically, centripetal force is directly proportional to the square of the velocity. This is crucial. If you double the speed of an object in circular motion, the required centripetal force doesn't just double, it quadruples. This highlights why high-speed rotations generate immense forces. These relationships are combined into a single power law formula. Fc equals m times v squared divided by r. Here, Fc is the centripetal force, m is the mass, v is the velocity, and r is the radius. It's important to note the typical units used in the ESA context for these calculations. Mass is often derived by dividing the object's weight in pounds by the acceleration due to gravity, approximately 32.2 feet per second squared. Velocity will be in feet per second and the radius in feet. Let's put the formula into practice with an example. Imagine a 10-pound weight moving in a circular path with a radius of 3 feet at a velocity of 500 feet per second. What would the centripetal force be? First, we need to convert the weight to mass by dividing 10 pounds by 32.2 feet per second squared. Then, we plug these values into our formula. Force equals mass times velocity squared divided by radius. So, it's 10 divided by 32.2 multiplied by 500 squared, all divided by 3. Performing this calculation gives us an approximate centripetal force of 25,880 pounds. Now, let's interpret what this means in terms of g-force. G-force is a measure of acceleration relative to Earth's gravity. If the object weighs 10 pounds normally, but effectively experiences an outward pull of 25,880 pounds, it means it's acting like it weighs 2,588 times more than it actually does. So, we can say the object is experiencing 2,580 Gs. This concept has critical real-world applications, especially in aviation. Consider the fan blades in a large turbofan engine. When that engine is operating at maximum revolutions per minute, the tips of those blades are moving at incredibly high velocities. Due to these immense speeds, the centripetal forces generated are enormous, causing the blades to experience thousands of Gs. This extreme force is why aerospace engineers must use incredibly strong, lightweight, and heat-resistant materials and design components with absolute precision to ensure they can withstand these stresses without failing. It's a prime example of physics directly impacting aircraft safety and performance. Now let's discuss periodic motion, specifically as it relates to pendulums. A pendulum is simply a weight hanging from a fixed point, free to swing. The period of a pendulum, represented by T, is the time it takes for it to complete one full swing back and forth. This period is primarily determined by two factors: the length of the pendulum, L, and the acceleration due to gravity, G. The formula shows this relationship. Notice that the period is directly proportional to the square root of the length. A longer pendulum will have a longer period. Interestingly, the period remains relatively constant even if the swing gradually becomes smaller. This consistent period is why pendulums were historically used to regulate the motion of mechanical clocks, providing a reliable timekeeping mechanism. Vibration is another form of periodic motion, often referred to as harmonic motion because of its regularity. The characteristics of vibration include the period, which is time for one cycle, the frequency, the number of cycles per second, and the amplitude, which is the maximum displacement from the center point. It's important to note that while the amplitude of a vibration typically decreases over time as energy is lost, the frequency remains constant. The formula for computing the period of a vibrating or oscillating object is conceptually similar to that of a pendulum. It is given by T equals 2 pi times the square root of m divided by k. Here, T represents the period of the oscillation. M is the mass of the vibrating object, and k, which is a force constant, is often referred to as the spring constant. It signifies the stiffness of the system. Vibration can be destructive in aircraft, so engineers must design aircraft to withstand or safely dissipate vibration from engines, components, or movement through the air. Resonance is the phenomenon where energy is transferred between two objects that have the same natural frequency. Every material has a natural frequency at which its atoms tend to vibrate. If one object vibrating at a particular frequency encounters another object with the same natural frequency, the first object can transfer its energy to the second, causing it to vibrate as well. A practical example of this in aviation is the avoid RPM ranges sometimes placarded on piston engine aircraft. Operating the engine within these ranges can cause the propeller tip speed to match the natural frequency of the propeller metal, leading to excessive vibration, dangerous stress buildup, and potentially catastrophic propeller failure. Now, let's explore the fascinating world of simple machines. A machine is defined as any device that helps accomplish work. There are several key functions that machines can perform. Firstly, they can transform energy. For instance, a generator transforms mechanical energy into electrical energy. Secondly, machines are capable of transferring energy from one location to another. This is evident in connecting rods and crankshafts, which transfer energy from an aircraft's engine to its propeller. Additionally, machines are designed to multiply force. A classic example is a system of pulleys that can lift a heavy load by applying a smaller force. They can also multiply speed, like a bicycle, which enables us to achieve greater speed with less pedaling effort. Furthermore, machines can change the direction of force, exemplified by the pag hoist, where a downward pull on one side lifts the load on the other side. There are 6 recognized simple machines: the lever, pulley, wheel and axle, inclined plane, screw, and gear. Interestingly, physicists identify only 2 basic principles in machines: the lever principle and the inclined plane principle, which underlie the operation of other machines. Now, let's continue with the concept of mechanical advantage in machines. Mechanical advantage, often abbreviated as MA, is a critical component in understanding how machines achieve their efficiency. It is defined as the comparison of the output force to the input force, or the output distance to the input distance. Machines serve to either multiply force, allowing us to achieve greater output than the input, or they can multiply speed, where one sacrifices force in favor of increased speed. However, it's essential to remember that a machine cannot multiply force and speed at the same time. Gaining one results in a loss of the other. To quantify mechanical advantage, we can utilize specific formulas. MA equals the output force divided by the input force, or the output distance divided by the input distance. These equations help us calculate how effectively a machine performs its work. Now, let's explore the concept of levers, one of the most basic and essential simple machines. Think of a seesaw. It perfectly demonstrates how a lever works. Every lever has 3 key parts: the fulcrum, which is the pivot point, the effort, which is the force you apply, and the resistance, which is the weight or force you're trying to move. The distances between the fulcrum and the effort and the fulcrum and the resistance are known as lever arms. The figure illustrates these components in a first-class lever. Torque, the force that causes rotation, is a fundamental principle in how levers operate. In a first-class lever, the fulcrum is positioned directly between the effort and the resistance. A seesaw perfectly exemplifies this. By adjusting the weight and the distance from the fulcrum, you can change the amount of force required. Increasing the lever arm on the effort side provides a greater mechanical advantage. Common examples of first-class levers include crowbars, shears, and pliers. Even balancing an airplane uses this principle, with the center of lift acting as the fulcrum. To calculate the force required, or the weight that can be lifted using a lever, we use the formula effort multiplied by the effort arm equals the resistance multiplied by the resistance arm. This essentially shows that the input torque equals the output torque. This principle applies to all types of levers and simple machines in general. Let's consider an example. If we need to lift a 500-pound weight with a lever where the resistance arm is 12 inches and the effort arm is 60 inches, we can calculate that only 100 pounds of effort is needed. This results in a mechanical advantage of 5, meaning you get 5 times the output force compared to your input. Now let's continue with second-class levers. In this type, the fulcrum is located at one end, the effort is applied at the opposite end, and the resistance is situated between them. A perfect example of a second-class lever is a wheelbarrow. The wheel acts as the fulcrum, The handles are where you apply the effort, and the bucket holds the resistance. The main benefit of second-class levers is their ability to amplify force, allowing you to move heavy loads with relatively little effort. Unlike first-class levers, however, second-class levers are only made to gain force. Let's look at another example, this time involving a wheelbarrow. If the distance from the wheel to the handles is 60 inches, and the weight in the bucket is 18 inches from the wheel, and we have 300 pounds in the bucket, we can calculate the force needed at the handles to lift the wheelbarrow is 90 pounds. The mechanical advantage in this case is approximately 3.33. Finally, we have third-class levers. These levers have the fulcrum at one end, the resistance at the other, and the effort applied in between. They are designed to increase the speed or distance of the resistance even if it requires a large amount of effort. A good example is the retractable landing gear on an aircraft, where the top of the gear acts as the fulcrum, the wheel and brake assembly is the resistance, and the hydraulic actuator in the middle is the applied effort. Now, let's explore the fundamentals of pulleys. At its core, a pulley is a simple machine, characterized by a grooved wheel, often referred to as a sheave, which is mounted on a fixed axis and supported by a frame known as a block. The primary purpose of pulleys is to assist in lifting or moving objects by either changing the direction of the force applied or by magnifying that force. When we combine a pair of these blocks, each housing one or more pulleys and connected by a rope, we form what is known as a block and tackle system. Next, let's delve into the single fixed pulley. This type of pulley functions much like a first-class lever, where both the effort arm and the resistance arm are equal to the radius of the pulley. Because of this equal arm configuration, a single fixed pulley provides a mechanical advantage of 1. This means the effort applied to the rope must be equal to the weight of the object being lifted. Therefore, its most significant advantage isn't to reduce the force, but rather to change the direction of the force, allowing you to pull downwards to lift an object upwards. This figure visually represents this setup. Now let's continue with the single movable pulley, which offers a different operational advantage. This pulley acts like a second-class lever, where the effort arm spans the entire diameter of the pulley, while the resistance arm is just the radius. This configuration gives it a mechanical advantage of 2, meaning it effectively magnifies the force exerted. For instance, if you're lifting a 100-pound object, you would only need to apply 50 pounds of effort. However, this force reduction comes with a trade-off. You'll need to pull the rope twice the distance the weight needs to travel. So, pulling 4 feet of rope will only raise the weight 2 feet. This figure illustrates this single movable pulley system. Finally, let's explore the block and tackle system. This advanced setup uses multiple pulleys, integrating both fixed and movable types to achieve higher mechanical advantages. The key to determining the mechanical advantage of a block and tackle is to count the number of ropes directly supporting the weight. As shown in this figure, if there are 4 ropes supporting the weight, the mechanical advantage is 4. This means that if you're lifting a 200-pound object, you would only need to apply 50 pounds of effort to raise it. This system demonstrates how combining pulleys can significantly reduce the force required for heavy lifting tasks. Now, let's explore the fundamental principles of gears as they apply to aircraft mechanics. Gears, like those shown in the figure, essentially act as levers. We distinguish between the drive gear, which provides the input force, and the driven gear, which receives that force. In this lever analogy, the diameter of the driven gear acts as the effort arm, and the drive gear's diameter serves as the resistance arm. It's also important to remember that when 2 gears mesh directly, they will rotate in opposite directions. Let's analyze a specific example using the spur gear shown. Imagine the larger, blue, 12-inch diameter gear is driving the smaller, yellow, 9-inch diameter gear. When we look at the mechanical advantage in terms of force, we divide the effort arm, the driven gear's diameter, by the resistance arm, the drive gear's diameter. This gives us a ratio of 9 divided by 12, or 0.75. This is a fractional disadvantage, meaning the output force will be less than the input force. Conversely, when considering the speed or distance advantage, we reverse this calculation. 12 divided by 9, resulting in a ratio of 1.33. This tells us that a larger gear driving a smaller gear results in higher rotational speed for the smaller gear, but with less available force. This leads us to a crucial concept: gear reduction. As we've seen, when a larger gear drives a smaller one, the smaller gear spins faster but with reduced force. For a system to be a force-gaining machine, the smaller gear must do the driving of the larger gear. In aviation, terms like propeller reduction gearbox indicate that the engine's input RPM is higher than the propeller's output RPM. This reduction in speed is precisely what allows for an increase in torque at the propeller, optimizing its performance. Now let's look at other types of gears. Bevel gears, as seen in the figure, are designed to alter the direction of rotation. For example, to connect a horizontal shaft to a vertical one. The ratio of teeth and size determines their mechanical advantage. If the gears have an equal number of teeth, they won't change the speed or force. The second figure illustrates a worm gear system. These systems provide very high mechanical advantages. A single rotation of the spiral worm can advance the spur gear by just one tooth. Consequently, the mechanical advantage is directly equal to the number of teeth on the spur gear, making it a very effective force-increasing mechanism. Now, let's explore planetary gear systems. This figure shows a planetary gear system, a configuration frequently found in propeller reduction gearboxes. This system typically involves a central sun gear, several planetary gears that orbit the sun, and an outer ring gear. In operation, the engine's output shaft drives the sun gear. This rotation causes the planetary gears to roll around the inside of the ring gear, which in turn rotates the output shaft. To determine the gear reduction, we divide the number of teeth on the ring gear by the number of teeth on the sun gear. In our example, with an 82-tooth ring gear and a 28-tooth sun gear, the gear reduction is 82 divided by 28, which equals 2.93. This signifies that the engine is rotating 2.93 times faster than the propeller. Now, let's clarify the terms velocity ratio and gear ratio. The gear ratio is straightforwardly calculated by comparing the number of teeth on the drive gear to the number of teeth on the driven gear. For instance, a 10-tooth pinion driving a 40-tooth spur gear has a gear ratio of 10 to 40. The velocity ratio or speed ratio is quite different. It compares the actual rotational speeds of the gears. Crucially, the velocity ratio is the inverse of the gear ratio. So, in our example, the speed ratio would be 40 to 10. This inverse relationship exists because as a gear's tooth count decreases, its rotational speed increases, and the opposite is also true. Let's work through an example to solidify our understanding of speed ratios. Suppose a pinion gear with 10 teeth is driving a spur gear that has 40 teeth and is rotating at 160 revolutions per minute. We want to find the speed of the pinion gear. We can use the relationship that the ratio of teeth is equal to the inverse ratio of their speeds. Plugging in our values, we have 10 teeth over 40 teeth equals 160 RPM over the speed of the pinion. Solving for the pinion speed, we multiply the number of teeth on the spur gear by its speed and then divide by the number of teeth on the pinion gear. This calculation shows that the pinion gear rotates at 640 RPM. Ratios are also fundamental for comparing different values, as shown in our next examples. First, let's consider an airplane's speeds. If its cruising speed is 200 knots and its maximum speed is 250 knots, the ratio of cruising speed to maximum speed is 200 to 250. Reducing this fraction to its simplest form gives us 4 over 5, or a ratio of 4 to 5. Our final example demonstrates how to express any ratio with a denominator of 1. To convert the ratio 9 to 5, we simply divide 9 by 5, which equals 1.8. Therefore, the ratio 9 to 5 is equivalent to 1.8 to 1. This concept of ratios is versatile and appears in many aspects of aircraft mechanics. Now, let's explore inclined planes, a simple machine that makes moving heavy objects easier. An inclined plane allows you to raise or lower heavy items by using a smaller force over a longer distance. Think of mountain highways or loading ramps on trucks. In aviation, we use ramps to get airplanes onto scales for weighing, which is much easier than jacking them up. The mechanical advantage of an inclined plane is derived from the ratio of its length, the effort arm, to its height, the resistance arm. Now, let's work through an example of how an inclined plane acts as a simple machine to make moving a heavy object much easier. We'll use the scenario of moving a Cessna 172 airplane, which weighs 1,600 pounds, up a maintenance ramp. The principle at work here is based on the law of moments, which states that effort multiplied by effort arm equals resistance multiplied by resistance arm. In this case, the resistance is the weight of the plane, 1,600 pounds. The resistance arm is the vertical height we need to lift it, which is the ramp height of 6 inches. The effort arm is the length of the slope we'll push along, which is the ramp length of 24 inches. Our goal is to find the effort required. So we set up our equation. Effort times 24 inches equals 1,600 pounds times 6 inches. To solve for effort, we calculate 1,600 times 6, which is 9,600, and then divide that by the length of the effort arm, 24 inches. This gives us a result of 400 pounds. Therefore, by using this ramp, an effort of only 400 pounds is needed to move the 1,600-pound airplane. The inclined plane reduces the required force by distributing the work over a longer distance, demonstrating a clear mechanical advantage. Now let's turn our attention to bolts and wedges, which also operate on the principle of inclined planes. A bolt has a spiral thread that runs around its circumference. The circumference acts as the effort arm, and the distance between threads is the resistance arm. Fine-threaded bolts have a greater mechanical advantage. A wedge, like a chisel, also uses this principle. The length of the chisel is the effort arm, and the width is the resistance arm. A chisel that is 8 inches long and half an inch wide would have a mechanical advantage of 16. Finally, let's consider efficiency. Mechanical efficiency refers to how well a machine uses the energy put into it. Losses due to heat, friction, deflection, and wear make machines less efficient. Efficiency is measured as a percentage, and no machine can be 100% efficient. We can calculate efficiency using formulas such as mechanical advantage divided by speed ratio, all multiplied by 100. Alternatively, we can divide the measured performance by the ideal performance to determine the efficiency of a machine. And that brings us to the end of this lesson for today. Now, let's warm up with a few questions to review what we've learned. Now let's get started with question 1. Which of the following best describes the difference between speed and velocity? A. Speed and velocity are the same thing. B. Speed refers to how fast an object is moving, while velocity refers to the direction an object is moving. C. Velocity refers to how fast an object is moving, while speed refers to the direction an object is moving. The correct answer is B. Speed refers to how fast an object is moving, while velocity refers to the direction an object is moving. Speed is a scalar quantity, meaning it only has magnitude, while velocity is a vector quantity, meaning it has both magnitude and direction. Question 2. An object is moving in a straight line at a constant speed of 20 meters per second, m per second. If the object accelerates to 40 meters per second in 10 seconds, what is its average acceleration? A. 2 meters per second. B. 4 meters per second. C. 20 meters per second. The correct answer is A. 2 meters per second. To find the average acceleration, we can use the formula. Average acceleration, A, equals final velocity, Vf, minus initial velocity, Vi, all over time. In this case, the initial velocity, vi, is 20 meters per second. The final velocity, vf, is 40 meters per second, and the time, t, is 10 seconds. Plugging these values into the formula, we get a equals 40 meters per second minus 20 meters per second, all over 10 seconds. A equals 20 meters per second, all over 10 seconds. A equals 2 meters per second squared. Therefore, the object's average acceleration is 2 meters per second squared. Question 3. A turbojet engine moves 200 pounds of air per second. Air enters at 200 fps and exits at 1400 fps. According to Newton's laws, what is the approximate thrust produced by the engine, in pounds? A. 6,211 pounds. B. 7,453 pounds. C. 8,124 pounds. Let's test your understanding of Newton's laws and their application to jet engine thrust. You are given the following information: weight of air moved per second, W, initial velocity of the air, VI, and final velocity of the air, VF. We want to calculate the thrust, F. To solve this, we use the formula derived from Newton's second law, F equals W, VF minus VI, divided by G times T. W, weight of air, equals 200 pounds. VF, final velocity, equals 1400 fps. VI, initial velocity, equals 200 fps. G, acceleration due to gravity, equals 32.2 feet per second squared. T, time, equals 1 second, since we're given the weight of air per second. Now, let's plug in the values. F equals 200 times 1400 minus 200, divided by 32.2 times 1. F equals 200 times 1200 divided by 32.2. F equals 2400,000 divided by 32.2. F approximately 7,453 pounds. Therefore, the correct answer is B, 7,453 pounds. This problem demonstrates how Newton's second law directly relates to calculating the thrust produced by a jet engine, specifically by considering the change in momentum of the air passing through it. Question 4. A 5-kilogram object is swung in a horizontal circle with a radius of 2 meters at a constant speed of 4 meters per second. What is the centripetal force acting on the object? A. 10 newtons, B. 20 newtons, C. 40 newtons. Okay, let's break down this question about centripetal force. Remember, centripetal force is the force that keeps an object moving in a circular path. Without it, the object would move in a straight line due to inertia. The formula for centripetal force, Fc, is Fc equals m times v squared divided by r, where m equals mass of the object in kilograms, v equals velocity of the object in meters per second, r equals radius of the circular path in meters. Let's plug in the values from the question. M equals 5 kilograms, v equals 4 meters per second, r equals 2 meters. So, Fc equals 5 kilograms times 4 meters per second squared divided by 2 meters equals 5 times 16 equals 80 divided by 2 equals 40 newtons. This corresponds to answer C, 40 newtons. Therefore, the correct answer is C, 40 newtons. Question 5. A mechanical clock uses a pendulum with a length of 10 meters. Assuming the acceleration due to gravity, g, is approximately 10 meters per second squared, and pi is approximately 3, what is the period, t, of this pendulum? A, 3 seconds, B, 6 seconds, C, 9 seconds. The question asks us to calculate the period of a pendulum given its length and using approximate values for g and pi. 1. Recall the formula. The period t of a simple pendulum is given by the formula T equals 2 pi square root of L over G, where T equals period, L length of the pendulum, G acceleration due to gravity, pi equals pi. From the question, we have L equals 10 meters, G approximately 10 meters per second squared, pi approximately 3. Let's plug these values into the formula. T equals 2 times 3 times square root of 10 meters over 10 meters per second squared. First, calculate the term inside the square root. 10 divided by 10 equals 1. Now, take the square root of 1. Square root of 1 equals 1. Finally, multiply everything together. T equals 2 times 3 times 1. T equals 6 seconds. Based on our calculation, the period of the pendulum is 6 seconds. Therefore, the correct option is B, 6 seconds. Question 6. According to physicists, which two fundamental principles form the basis for all simple machines? A. Pulley and wheel and axle. B. Screw and wedge. C. Lever and inclined plane. The correct option is C. Lever and inclined plane. Remember, while we commonly identify 6 simple machines, the lever, pulley, wheel and axle, inclined plane, screw and gear, physicists simplify this classification. They recognize only 2 basic principles upon which all these machines operate: the lever and the inclined plane. The pulley, wheel and axle, and gears are considered applications of the lever principle, while the wedge and screw derive from the inclined plane. Question 7. A first-class lever is designed to lift a 400-pound resistance. If the resistance arm is 8 inches long and an effort of 80 pounds is applied, what is the required length of the effort arm? A. 40 inches, B. 50 inches, C. 60 inches. To solve this, we apply the principle of moments, which states that input torque equals output torque for a balanced lever. The formula is effort, E, times effort arm, L, equals resistance, R, times resistance arm. We are given resistance, R, equals 400 pounds. Resistance arm, little, equals 8 inches. Effort, E, equals 80 pounds. Plugging these values into the formula, 80 lb times L equals 400 lb times 8 inches. 80 L equals 3200. L equals 3200 divided by 80. L equals 40 inches. So, the required length of the effort arm is 40 inches. Question 8. Consider a wheelbarrow. Which class of lever does it represent based on the arrangement of its fulcrum, effort, and resistance? A. First-class lever. B. Second-class lever. C. Third-class lever. The correct option is B. Second-class lever. Let's break down the components of a wheelbarrow in terms of a lever. The wheel acts as the pivot point or fulcrum at one end. The effort is applied at the handles at the opposite end. The load or resistance is placed in the bucket, which is located between the fulcrum, the wheel, and the effort, the handles. This arrangement, where the resistance is between the fulcrum and the effort, is the defining characteristic of a second-class lever. Question 9. Which type of pulley is best described as a first-class lever with equal arms, offering a mechanical advantage of 1 and primarily changing the direction of the force exerted? A. Single fixed pulley. B. Single movable pulley. C. Block and tackle system. Let's review the characteristics of our different pulley types. The correct answer here is A. Single fixed pulley. This type of pulley functions much like a first-class lever where both the effort and resistance arms are equal to the pulley's radius. Because of this, its mechanical advantage is exactly 1, meaning you'll need to apply a force equal to the weight you're lifting. Its main benefit isn't to magnify force, but to simply change the direction of your pull, making lifting easier or more convenient from a different angle. Option B, the single movable pulley, actually magnifies force and acts more like a second-class lever. And option C, the block and tackle system, involves multiple pulleys to achieve a greater mechanical advantage, typically much higher than 1. Question 10. Which type of gear system is characterized by an extremely high mechanical advantage where one complete revolution of the input element only moves the output gear by a single tooth? A. Bevel gear, B. Worm gear, C. Planetary sun gear. The correct answer is B. Worm gear. Let's review why. The content describes the worm gear as having an extremely high mechanical advantage. It states, one complete revolution of the worm gear only makes the spur gear turn an amount equal to one tooth. This unique characteristic makes it a force-gaining machine with a significant increase in output force often equal to the number of teeth on the spur gear it drives. A. Bevel gears are primarily used to change the plane of rotation, allowing a horizontal shaft to drive a vertical one or vice versa. While they can provide mechanical advantage, their defining characteristic isn't the single-tooth movement per revolution like the worm gear. C. Planetary sun gear systems are typically found in reduction gearboxes like those for propellers. They involve a central sun gear, planetary gears, and a ring gear, designed to reduce RPM and increase torque, but they don't operate on the principle of one revolution for one tooth movement. Question 11. A small drive gear with 15 teeth is driving a larger driven gear with 60 teeth. If the driven gear is rotating at 120 RPM, what is the rotational speed of the drive gear? A. 30 RPM, B. 240 RPM, C. 480 RPM. The correct answer is C. 480 RPM. To solve this, we use the relationship between the number of teeth and the rotational speed, which is described as the inverse of the gear ratio. The principle is number of teeth on drive gear divided by number of teeth on driven gear equals speed of driven gear divided by speed of drive gear. Let's plug in the given values. Teeth on drive gear equals 15. Teeth on driven gear equals 60. Speed of driven gear equals 120 RPM. Speed of drive gear equals unknown, let's call it S drive. So the equation becomes 15 over 60 equals 120 over S drive. First, simplify the fraction 15 over 60, which reduces to 1/4. 1/4 equals 120 over S drive. Now, to find S drive, we can cross multiply. 1 times S drive equals 4 times 120. S drive equals 480. Therefore, the rotational speed of the drive gear is 480 RPM. This makes sense because the drive gear has fewer teeth, so it must rotate faster to drive the larger, slower-moving driven gear. Question 12. An engineer needs to push a heavy component weighing 2,000 pounds up a ramp onto a work platform. If the ramp is 8 inches high and has a length of 32 inches, what force, effort, is required to push the component up the ramp? A. 400 pounds, B. 500 pounds, C. 600 pounds. To determine the force required, we apply the fundamental principle of the inclined plane, which is derived from the work energy principle. The formula we use is effort, E, times effort arm, L, equals resistance, R, times resistance arm. Let's identify our known values in this scenario. The resistance, R, is the weight of the component, which is 2,000 pounds. The resistance arm, L, is the vertical height of the ramp, which is 8 inches. The effort arm, L, is the length of the ramp, which is 32 inches. Now substitute these values into the formula. E times 32 inch equals 2,000 pounds times 8 inch. To solve for the effort, E, we rearrange the equation. E equals 2,000 pounds times 8 inch divided by 32 inch. E equals 16,000 pounds inch divided by 32 inch. E equals 500 pounds. Therefore, the force, effort, required to push the component up the ramp is 500 pounds. The correct answer is B. This calculation clearly illustrates the mechanical advantage gained by using an inclined plane. allowing a heavy object to be moved with a significantly smaller applied force over a longer distance. Question 13. When considering a boat as an inclined plane, which of the following represents the effort arm? A. The distance between the threads. B. The circumference of the boat. C. The overall length of the boat. A boat is an excellent example of a device that operates on the principle of an inclined plane. Its spiral thread effectively acts as a continuous ramp winding around a cylinder. To understand its mechanical advantage, we relate its geometry to the effort and resistance arms. The effort arm is the distance over which the effort is applied. When you turn a boat, the force is applied along the path of the thread as it winds around the boat. This path corresponds to the circumference of the boat. The resistance arm is the vertical distance the boat advances for one full rotation. This distance is the space between consecutive threads, also known as the pitch of the thread. So, for a boat acting as an inclined plane, the circumference of the boat represents the effort arm, allowing a rotational force to be converted into a linear force, thereby providing mechanical advantage. The correct answer is B. That's all for today's lesson. If you found this video helpful, please give it a thumbs up and consider subscribing to Airwise Academy for more aviation knowledge. We'd love to hear your thoughts or questions in the comments below. Turn on notifications so you won't miss our upcoming videos. Until next time, blue skies and happy learning!